Hi, Philip here. This is going to be the Chapter 26 homework preview. And the problems I'm planning to help you set up are number 3, 8, 25 and 26, they kind of go together, and 27 and 28, they're kind of follow-up problems from those two. 3 will also help you with number 4, and these ones, they're about capacitors, will also help you with a bunch later on. Then in the second video, in the second part, I'm going to go through 46, 47, and 67. And in the final one, I'm just going to look at 81, which is, I guess, the challenge problem of this week's homework. Let's get started. This is number 3. You're given a graph, and the graph shows you the electric field as a function of position. Specifically, it shows you the x component of the electric field. So you get this graph. Here I try to sketch what that looks like, right? So you've got the x component of your electric field is, the x-axis is this way, then it is this sort of sideways component. And at x equals 0, the field is strong, it's 200 volts per meter. At x equals 1, it's down to 100. At x equals 2, it's 0, there's no field here, so somewhere here at x equals 2, there's no field. And then the field here is negative, or the x component of the field is negative, which means it points backwards. So we are asked to find the potential difference from here to here, on the graph from here to here. So we're going to use the connection between the potential difference and the electric field. The hard part here is how do we interpret this? So the integral is always taken from the start point to the end point, of course. And what we're really doing is we are taking tiny little steps along some path, and for each step we're adding up how much we're going up or down in the potential. Right? Because the electric field gives us the rate of change of potential with distance. So we take the rate of change of potential with distance, if you like, the slope of our potential, and just multiply it by our step size, taking into account that the direction might be up or down or at some angle, right? And so the dot product ensures we're taking the component of our step in the direction of the electric field. Now in this case, let's make sense of this. We're going to start at x equals 0. We're ending at x equals 3, right? We're told those are the points between which we're trying to find the potential difference. The electric field is given right here, the x component of it, and then we're going to do our steps. Now, because we're stepping along we're calculating the potential difference along the x-axis, a little step ds, this sort of general expression for take a small step in some direction, well, it is just dx. Right? Because our path is just in a straight line from here to here. Now, in general, we could have added, let me just write down the more general form, where the dot product here could be written as this, plus ey dy plus ez dz. So in general, this is a line integral. If you've met the concept before in some more advanced calculus course. This would be the general case if our path was not along the x-axis, but sort of, some kind of curved path from one point to the other. Well, along each step, we might change our x position a bit, our y position a bit, our z position a bit. And to figure out are we going up or down in the potential, we'd have to multiply each direction with the corresponding gradient of electric field in that direction. But in our case, these ones are the 0 by our choice of path. Because we're going just along the x-axis. Sorry, along x-axis this is. By choice of path along the x-axis. Right, so we can forget about these parts here. So you just have to evaluate the integral from x equals 0 to x equals 3 in this way. So now all you have to do is you have to figure out what is this. And there are two ways you can actually solve this. One way is you find an explicit function for this, and you get that from the graph, right? So you could, it's a straight line, it's going to be a linear function. Put the coefficient where it crosses the axis, what's the slope, you can figure it out, make sure you pay attention to the sign. The alternative way is to realize that an integral of something dx is, if you put x on this axis and the something on this axis, it's just the area under the graph. So your answer is going to be this area here, again paying attention to the sign in this area here. Hopefully it'll help. And number 4 works pretty much the same way, except there your function looks a teensy bit more complicated, though it's again linear, you just have to split it up into 2. Okay. So you figure out the rest. You figure out what is this expression, if you want to do it algebraically, or you just figure out what's the area under this graph, if you want to do it, let's call it geometrically. That is number 4 for you. Let's move on. Here's the setup for number 8. In this case, we're given a chart that has x and y, so this is more like a map, right, that we're looking at. It's not a graph of y against x. It's a coordinate system looking at a map, and what's shown us is equipotential lines at minus 200 volts, 0 volts, and 200 volts. What we're asked to find is the electric field at this point here. Now, the electric field is the downhill slope of the potential. So which way is downhill? Well, if you think of those as altitudes, right, the side of a mountain, they're straight lines. It's just this way is down, this way is up. So right here, electric field is always perpendicular to the equipotential line. It's going to point necessarily in this direction, because these lines are 45 degrees to the x and the y axis. This is going to be 45 degrees the other way, right? So this is perpendicular here. How strong is it? Well, the electric field strength, E, is the slope, right? Now you could work out an x and y component and make your life hard, but here, essentially, because it's such a simple scenario, right, with parallel lines of constant height, that is straight lines, you can just read off what the slope is. Right? If you go in the direction of the field, right, like this, the field strength, go in the direction of the field, you take a 1 centimeter step, 1 centimeter, we're given that, you go down by 200 volts. Take a 1 centimeter step the other way, you go up by 200 volts. So the slope is 200 volts per centimeter. Well, you can figure out what it is in standard units of volts per meter. And that's all there is to it. That's 26.8. You just fill in the little gaps, but that's pretty much it. Let's go on to the next one. And we're on to number 25. So the setup for 25 is that you have 3 capacitors of different capacitance. It gives you values. I'm not going to work with the values. I'll work with, general capacitance C1, C2, C3. If you can't remember what capacitance is, please read the relevant section in the book or watch the video where I introduce it. So when it says they're connected in series, what this means is that you're essentially connecting them one after another. So you're connecting, maybe there's a battery or something over here, who knows what's happening, but there's a capacitor here, and then the one end of this capacitor is connected with a wire to the next one. And then this one is connected to the next one, right? And then it goes and does something else. So normally we have the capacitance, and C is the charge stored divided by the potential difference. So in this case, what you're going to get is you're going to get a certain amount of charge that's stored here on this plate, and then say this is positive, then there's the same amount of negative charge on the other plate. If this wasn't the case, if there was more positive here than negative here, well then this extra positive would attract some more negative ones to enter the plate until those are balanced out. Now because this middle piece of wire, right, it's a conductor, so electrons can flow around inside, it's isolated from the rest of the universe, so electrons can't sort of just enter from anywhere else, it's not, say, grounded. That implies that if there's a charge build-up here, say a bunch of electrons have moved into this plate, the same number of electrons is missing on the other side, missing over here. So that implies that there's the same amount of charge on this plate, negative charge extra here, as is missing here. So there's minus Q here, is plus Q, it's the same Q from one capacitor to the next. Because the overall, this sort of central piece of two plates connected by a wire, right, it is neutral. So if you build up charges in one place, you're going to steal them from somewhere else. Same thing from going from here to here. So then what you have is you have an electric field between each pair of plates. And so what you're going to get is, of course, you're going to get a potential difference from one side to the other. From one side to the other. So let me put that in red. Going from this side to this side, we're going to get a certain potential difference, delta V1. We're going to get a certain potential difference, delta V2. We're going to get a certain potential difference, delta V3. We're going to assume those wires are perfect wires. That is a general assumption. Otherwise, you'd sort of build resistors into it. But we're going to come to that later in the course. Right now, we're just assuming it's the perfect wires, which means electrons are free to move, within them any way they want. And one implication of that is there's no potential difference, right, from this side to the other side. Because they're perfect conductor, and inside a perfect conductor there's not going to be any electric field. So no potential difference. Okay, so capacitance is defined as charge per delta V. So we've got 3 delta V's, and then the combined capacitance of those is essentially saying, well, what is the total potential difference from here to here? Right, so you go from here to here, call this delta V total. Right, this delta V and those charges that are held Q, right, those are going to define the overall capacitance of this setup. You could sort of imagine, if you could trouble sort of understanding what I'm trying to say here, imagine there's some sort of black box around this, you can't look inside. There are 3 capacitors inside, but you don't know, is it 3 capacitors, is it 1 capacitor? You don't know what's inside, but you can say, okay, there's a certain potential difference from here to here, there's a certain amount of charge that has entered that box on the one side, and the same amount of charge has come out the other side, or vice versa, so that you have an amount of charge and a total potential difference. So we've got this, right, it's our definition of capacitance, and so if I want to express the delta V in terms of Q and C, I might just write delta V is Q over C. So what I have is I've got delta V1 is Q over C1, delta V2 is Q over C2, and delta V3 is Q over C3, right? For each capacitor, I can write down what do we mean by the capacitance of that capacitor. But then I also can write down total delta V from all the way to the left to all the way to the right. Well, it's going to be Q divided by the total C, the combined C. So that's the thing I want to find. And of course, the total potential difference is going to be the sum of the individual potential difference, right? This is equal to delta V1 plus delta V2 plus delta V3, right? Because you imagine the field points downhill, so sort of you're walking along at constant voltage, constant altitude if you like, and now there's a staircase down, and it's again flat, 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 no change in height, no change in voltage, right? Down, 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 down in terms of the voltage, and it's flat, 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 no voltage change, down, down, down. So the total distance we've gone down is how much you've gone down here, plus how much you've gone down here, plus how much you've gone down here, right? That analogy between altitude and potential, it still works. Okay, so now you've got this, and you've got this, and you've got an expression for each of those. So what do we get when you plug these ones into here and set that equal to this? We're going to get that Q over C1 plus Q over C2 plus Q over C3. And of course, if I had more capacitors, say 4, 5, 10, 100, right, I'll just add more in this list. That is equal to Q over C total. And of course, you can factor out a Q and cancel it out really. So what you get is that 1 over C total is going to be equal to 1 over C1 plus 1 over C2 plus 1 over C3. And if there's more, there's more, right? In our case, there isn't. But if there were more capacitors, we just keep going. So this gives you an expression of the effective capacitance of those capacitors put together in series. So make sure you understand the logic here. But now that you've derived this, or we've derived this, right, you can just apply it when you see a bunch of capacitors in series. You don't every time have to sort of derive it from scratch, although you should understand how to do this. Now let's look at the other case, 6.26, where we look at capacitors that are connected in parallel. Here's my drawing for number 26. So being connected in parallel means that they're connected with wires, with some conductor, in such a way that if you were an electron traveling along, right, and you could sort of pick one, and then if you could hop across it, right, you only would have to choose one to get from one side to the other. Right? Whereas when they were connected in series, you kind of have to travel through all three of them if you wanted to go from the left to the right. In this case, you get a choice. They're connected in parallel because there are like three of them in parallel. The way I've drawn it literally, they're the parallel lines. Realistically, that they don't have to be actually geometrically parallel lines, but they have to be connected in such a way that you could draw it like that. Okay, so the crucial thing here is that if those are perfect wires, right, and that's the assumption unless it tells you otherwise, then that implies there's no electric field inside these wires. I just draw them as lines. That's what we do with wires. That means the potential anywhere on the left is the same as anywhere else on the left. So let me see if I can maybe use some color here. So here, let me do it like this. Make those purple. So all those purple parts, they're all the same, at the same potential, right? The same altitude, if I go with that analogy again. Similarly, on the right, all these wires here that I'm now drawing in blue, they are all the same potential to each other. Right? Of course, the potential here is different from here because the potential drop across each capacitor. But because the potential in all the purple ones and all the blue ones is the same each, it means the potential difference is the same. Sort of like you march along here at a constant height, and you've got a choice of going down the elevator here, or the elevator here to end up on the other side, but you're going to end up at the same final height. Right? Because there can't be a potential difference between here and here, because going along the wire, there's no electric field anywhere, because it's a conductor. So this is delta V3, this is delta V2, and this is delta V1, denoting the potential difference, then I get that delta V1 equals delta V2 equals delta V3. What's not the case here, in contrast to the previous question, is that the charges have to be the same, right? They very much don't. It could be very different from each other. Now, if all those capacitors, say they're parallel plate capacitors, that's how I've drawn them. That's how you draw them no matter what type of capacitor they actually are. You always draw them symbolically as parallel plate capacitors. Let's assume they actually are. Let's assume they're the same distance apart. Then it's almost like I'm just adding the area of this one to the area of this one to the area of this one when it comes to holding charge. And since a parallel plate capacitor is proportional to the area of the plate, well, you're just adding the areas for holding the total charge, so you're just adding the capacitance. It turns out to be true, but let's actually prove this. So I know that those ones are the same, and again, I want to find the total capacitance. So capacitance is going to be the total charge held divided by the potential difference. Potential difference here is just, any one of them. They're all the same. This is the potential difference from here to here. It's just one value, right? And it's 5 volts, 5 volts, 5 volts, while the potential difference is 5 volts, right? So let's just call it just delta V, right? Without a subscript, because they're all the same. What is Q total? Q total is Q1 plus Q2 plus Q3. It's the total charge held by the left-hand side and negative on the right-hand side. By delta V. That, of course, I can write as Q1 over delta V plus Q2 over delta V. I guess V1 plus Q3 over delta V3. I'm going to put this in parentheses because all the delta V's are the same, right? So whether or not I have a subscript here or not doesn't really matter. I'm writing it with the subscript. This is the same as this, the same as this, the same as this. This is why I can write this expression as this expression here. But by writing it with the subscript, we can very much see that this is just C1, charge on capacitor 1 per voltage across capacitor 1, plus C2 plus C3. So when capacitors are put into parallel, connected up like this, with the conductors, usually a wire, then the capacitances just add. Right? We don't have to make assumption about there being parallel plate capacitors and the same distances, the same plate distance, so you can just add the areas. That's conceptually useful, but we can just prove it like this, that the total capacitance is just the sum of the individual capacitances. So that will allow you to solve problem 26 fairly straightforwardly. You just have to plug in numbers, really. And those insights from 25 and 26, they will also help you with a bunch of other problems on the homework. Let's move on to two of them where you're going to apply these same ideas. Here's number 27. In number 27, you're given a circuit map of three capacitors. They're hooked up by wires in this particular way. So you now know how to deal with capacitors in parallel and in series, but this one is kind of a mix of the two, right? So here's how you decompose these kinds of diagrams. So the wires, okay, they're just wires. So you look, essentially, the paths you might go down. And what you notice is, you might ask this, so is this one in series with this, or this one in series with this? What about those two? Looks like they're in parallel, but like how do I go about thinking about this? So the way to think about this is, okay, imagine you walk along, you say, okay, I have to jump over this one, but here I get a choice, right? Look at how the wires are connected, and you're like, okay, well, this area here, and I'm going to color those in, that's all the same the same potential, and this area down here is all the same potential. Just because they're connected with wires, no electric field in the wire, no potential difference from one part of the wire to another connected part. So that tells you that those two have the same delta V, right? They are in parallel. This one is not in parallel with this one because the charge on here is probably not equal to the charge on here. I mean, minus Q here is not the same Q as plus Q here, because there's also this one, right? Charges, they spread themselves out on here and here. So this one is not in series with either this one or this one, but once you've combined them, these two, we know how to deal with parallel resistors, parallel capacitors, how to represent them as a single capacitor, then this one here is essentially in series with that combined one here. So the fact that they're the same delta V, that implies C2 and C3 are in parallel. So what does that mean? You know how to deal with parallel capacitors. Their capacitances just add. So we can take this thing here and we can represent as the following. We can say, okay, there's this capacitor up here, but now we just represent those two parallel ones as a single one with capacitance C2 plus C3. C1 hasn't changed, and now you can clearly see, okay, C1 is in series with those two. This is a combined capacitor, right? Treating those two as just one. But you have to do the steps in that order, right? The other way around will simply not work. Right here you see, okay, the charge here is the same as the charge here. Oh, no. This one is Q minus Q. This one is, again, plus Q minus Q. Because this piece of wire here is isolated from everything else. Any charge that moves into here has to be stolen from here. Okay, let's look at 26.28, which is a very similar question. In 26.28, you have a setup where with one capacitor, two capacitors, and it goes back to the battery, but we don't really care about that right now. And you've got another one over here. And again, you're given numerical values for the capacitances, but let's not worry about that. So, what do you observe? Well, you observe that because this middle piece here is isolated, right, it's not touching any other conductor, you must have, let's say, if this is a plus Q minus Q, 1, 1, you get plus Q 2, but that's equal to plus Q1, right? Those two are the same because any electron that entered here must have been stolen from here. So then we get minus Q2, and that is going to be equal to minus Q1. So in this case, we start out with these one in series, right? And so you can rewrite this then as, as having one capacitor here, second capacitor here, this is C3, and then this is the combined C. Now because they're in series, they don't add, right? It's not C1 plus C2. The combined capacitance is 1 over C combined, is 1 over C1 plus 1 over C2, right? That's what we learned in a previous question. So this here is the C combined. So you work it out and you work out this, right? But then you actually want the value of this, not 1 over this. And now you've got those two in parallel. because all these wires up here have the same potential, and all those wires down here have the same potential. Right, so these ones are now in parallel, and so you can find the overall effective capacitance of this circuit as well. We're going to use very similar techniques when we talk about resistor circuits in a couple of weeks. But hopefully this makes sense to you. There are a couple more capacitor questions on the homework, but with those tools you now have, they shouldn't be very difficult. Good luck. In parts 2 and 3 of this homework review, I'm going to go through some other questions that are not about capacitor circuits. I will see you there.